Physics review, first 6 weeks. All right, start off with units of measure versus variables and equations. All right, so we can use equations to answer questions using measured variables in an experiment or given variables in a question. It's important to know that the variables your class uses in units will help you determine equations to use. While the physics stays the same, different textbook may also use different letters to represent variables of the same equation. For example, displacement can be represented by D, but it can also be represented by an uppercase letter X. So let's talk about some fundamental units. We got length, mass, and time that we've covered so far. So for length, the quantities, we've got meters represented by an M, kilometers represented by a km, feet represented by ft, miles represented by mi. Mass, we've got grams represented by a g, kilograms represented by a kg. Important thing about mass is it's the quantity of matter of an object. Don't confuse this with weight. Weight is a force, and we're not there yet, but we'll get there. Time, you got seconds with S, minutes with MIN, hours with HR. So some common metric prefixes, if you'll notice, like meters to kilometers, grams to kilograms. A kilometer is 1,000 meters. A kilogram is 1,000 grams. Some other prefixes are mega, centi, milli, micro. Coming down to some equations. We'll get to these as we go along. This is velocity average, change in position over time. Velocity average, take that one away. Add initial velocity and final velocity and divide by time. Acceleration, change in velocity over time. So that's the final velocity minus the initial velocity divided by time. These are kinematic equations. Velocity final is equal to velocity initial plus acceleration times time. Our velocity final squared is equal to our velocity initial squared plus 2 times our displacement or change in position, as this is written. Our displacement or change in position is equal to our initial velocity times time plus 1/2 our acceleration times time squared. Solving for position, it is our velocity initial plus our velocity final divided by 2 multiplied by the time. All right. Those equations will come up again later, so we'll move on through the material. All right. Accuracy refers to how close a measurement is to the true or accepted value, where precision refers to how close measurements of the same item are to each other. So you'll notice the first picture here is accurate but not precise, while the second picture is precise and accurate. They're all near the bullseye where we're aiming. This picture down here is not accurate, nor is it precise. It's just scattered all around. There's no sort of grouping. Down here we've got precise but not accurate. You'll notice as we go up this pictures, the accuracy is higher in these two. As we go right, the precision is higher there. Down here, we're lowest of both. All right, so moving on, order of operations. Got what we call PEMDAS. What everybody likes to forget is multiplication, division, and addition, subtraction are grouped together. You'll notice the color scheme here. Your first order of operations is what's inside the parentheses. Your second order of operations is things that have exponents. Your third order of operations is multiplication or division. You go left to right, just whatever is first. Your next order of operations is in addition or subtraction. It's also the last one. Again, left to right. So, significant figures and rounding. All right, so there's a neat trick here, the decimal versus no decimal method. So if there's a decimal, you're going to start at the left, and you're going to begin counting at the first non-zero number and count all numbers after. If there's no decimal, you're going to start at the right, and this time you're going to begin counting again at the first non-zero number and count all numbers after. So that's the neat trick, going left to right. But as far as like the standard rules for significant figures, all non-zero numbers are significant. Zeros between two non-zero digits are significant. Leading zeros, not significant. Trailing zeros to the right of the decimal are significant. Trailing zeros in a whole number with the decimal shown are significant. So if we follow our two rules above, decimal versus no decimal, these 5 rules below will be met. All right. So let's look at an example with significant figures. So when we talk about rounding, right, we're gonna say, well, the numbers we're working with, the value we're working with, only has 2 significant digits. So our answer should be 1.4, 2 significant digits, not 1.428571428574143, which is 15 significant digits. So suppose you're told that a skater traveled 10 meters in 7 seconds. So we'll notice that one of these numbers has 3 significant figures, one of these has 2, right? So the rule is you multiply or divide these numbers. The resulting number has significant figures equal to the smallest number of significant figures in any of the original numbers in the problem, in the numbers that we use to solve. So if you want to figure out how fast the skater was going, we're dividing 10 by 7, the meters by seconds, and the result should have only 2 significant digits or 2 significant figures. So we should have 1.4 meters per second as our answer. Again, not the 1.428571428574143. All right, so scientific notation is just a way to write very large or very small numbers in a compact way without removing any significant figures from those numbers that we write. So we're going to move the decimal to the right or to the left to arrange it to where there's 1 digit to the left of the decimal point. Therefore, the numbers between between 1.0 and 9.9. So, example here, 52,314, 5.2314 times 10 to the 4th. Notice it was moved 4 places. 3.2, we don't have to move it at all, so it's 3.4 times 10 to the 0. That exponent pounder 0 makes this just 1. 3.2 times 1 is 3.2. All right, so here we got a small number. We need to move it right 5 places. 4.28 times 10 to the negative 5th. Down here we've got 602 million. We need to move it 8 places. We've got 6.02 times 10 to the 8th. Notice our significant figures don't change. 5 here, there's 5 here. 2 here, there's 2 here. 3 here, because there's our decimal. We don't start counting until we get to that 4. 1, 2, 3 sig figs. There we go. Here we start counting from this direction. Don't start till we get to the 2. 1, 2, 3. They all count. There they 3 still are. Still same significant figures. Another example over here where you're actually showing being counted the spaces. Fill them back in with zeros if you're coming up. Take away the zeros if you're going down. All right, so what are we doing in a sense? We're multiplying by powers of 10 to make these large numbers, or we're dividing by powers of 10 to make these small numbers. These negative exponents are just representing division by levels of 10. Okay, and again, here's another example of a small number being wrote in significant figures, or excuse me, in scientific notation. All right, so coming down, dimensional analysis, unit conversion. So let's say we've got a unit and we want to convert it to another unit, right? So we're going to convert this unit to measurement. So we're going to multiply by a conversion factor. It's a ratio expressing how much of one unit are equal to another unit. It's simply rewriting the number 1 in a fraction of 2 different things. And you'll see here we've got the number of units we have, and so we're going to put the units we have down at the bottom and how its ratio is with the units that we want. So then when we come down here, let's look at an example to make a little more sense. So let's say you have 652 miles from Atlanta to where you're asked to convert this, right? You're asked to convert this 652 miles distance to Atlanta into meters, right? So there we go. We've got the units we have, 652 miles. Down here, we're going to put the units we have, 1 mile. Well, our conversion factor here is 1 mile is 1,609.34 meters in this instance. So we put that up top. Notice our miles over miles cancel out, just like dividing 3 by 3 is 1. Miles divided by miles is also 1, canceled out. So what we do is everything on top we multiply, everything on bottom we divide. So we multiply 652 by 1609.34. We divide by this arbitrary 1, but in some instances this is not going to be 1. So we divide by that 1 and we get our number. But we have to remember the significant figures from above. because of our significant figures only being 3 here and 6 in our conversion factor, well, let's just worry about this 3, okay? So we're going to round this to 3 significant figures. So we're going to have, what is this? 1,050,000, right? And with our proper significant figures, now if we need to write that in scientific notation, boom, 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 moved it 6 places over, 1.05 times 10 to the 6th. There's our 2 answers. Both those answers are correct equally. Depends on if we want it written in the longhand form or we want to write this in scientific notation. So moving right along, we've got scalars and vectors. So a scalar in physics includes only a magnitude. Magnitude is a number and a unit. 2 common scalars are distance, for example 5 meters, and speed, for example 5 meters per second. Speed is a scalar because it uses that scalar distance traveled per unit of time, so distance per time. So a vector in physics has a magnitude and direction. If you'll remember from Despicable Me, you've got Vector the villain. He's committing crime with both direction and magnitude. So 2 common vectors are displacement, 5 meters east, and velocity, 5 meters per second east. Notice we use the same magnitudes from above, but we added a direction to those things and they're vectors. All right, so what is distance? Distance, the scalar, like we just said, is a measure between 2 points. Distance has no direction. We add it all up, right? So here we go. We got the guy walking. We just add up everything that he walks. He walks 6 out. He walks back the 4. Therefore, he walked a total of 10 meters. But with displacement, a vector quantity, it's just a measure of where you are from the origin or your starting point and in what direction. So it's the difference in between where you start and where you finish, and it has a direction. So coming down, got displacement. Again, he walks out to 6. He walks back to 2, but this time we take away those 4. Because if we were to close our eyes when he started and then open our eyes when he finished, he would only be 2 meters away to the right. He would just have that 2 meter right displacement in this instance. All right. So speed versus velocity. So speed is a scalar. Scalars go with scalars. We use distance to calculate speed as seen in the equation on the right. Speed is distance divided by time. Vectors, however, go with vectors. So we use displacement to calculate velocity. Ironically, speed starts with an S, scalar starts with an S, vector starts with a V, velocity starts with a V. Velocity is displacement divided by time. So there we go. We've seen those equations again. Better start jotting them down. All right, so acceleration. Velocity is how far we're traveling from our starting point during a time period, including our direction, right? So if our velocity never changes, you're traveling at a constant velocity. But what happens if that velocity does change? Well, that's called acceleration. It describes how velocity changes from our initial velocity during a time period, over a period of time. So you can accelerate by going faster. You can accelerate by going forward, or by going slower. We also call that deceleration. Or you can simply change the direction. Remember that velocity was that vector quantity. It had magnitude and direction. We can change the magnitude component or we can change the direction component of our velocity. Since this acceleration describes a velocity change over time, over a period of time, the acceleration unit we'll use includes the unit for velocity, meter per second over a time period of seconds. Therefore, we write this as meters per second, or commonly meters per second squared. Acceleration is also a vector. It would include direction that the velocity is changing. So we're going to come down here. We're going to look at a couple examples of acceleration. Notice the guy in this first video here is moving along more and more and more rapidly. He's accelerating at 0.5 meters per second every second. So after 1 second, he's going 0.5. After 2, he's going 1. After 8, he's going 4. He's just speeding up by 0.5 every second that he moves. All right, over here we've got an example of constant velocity where the gentleman is just walking along versus someone who's accelerating, walking very slowly in the beginning, very rapidly in the end. All right, so let's look at some graphs. Position versus time graphs, or PT graphs. So position versus time graphs show how displacement changes in our y-axis relative to time in our x-axis. Don't worry, there'll be some examples. Since slope equals rise over run, and since rise is change in displacement and our run is change in time, the slope of our PT graph is our velocity. It's that displacement over time we just talked about for the velocity equation. So be aware that the position and the displacement are used here interchangeably as, again, that uppercase letter X variables. Position means where you are located, and displacement means how far you are from your prior position with a direction from start to finish. Very key there. All right, so total displacement equals final position minus our initial position. So our displacement X, or also written with a D, can be our position final minus our initial position, the X subscript F minus the X subscript I, lowercase x for displacement here. Actually, it should be an uppercase x. But, all right, so what does the slope of a PT graph represent? So if we get a flat line in our PT graph, it shows no slope, meaning no motion. The object is at rest. The velocity is 0. It's just the same position every time we put a little dot on the graph. What is a positive slope represented in a PT graph? It represents a constant velocity, a plus constant velocity. What is a negative slope? It represents a constant backward motion, a constant negative velocity. And a curved line represents an acceleration or deceleration. We have something speeding up, or we have something slowing down. Below, we'll have some examples. And here they come. All right. So like I said, no motion would just be a flat line. Don't have that represented here. But we've got this constant velocity, constant positive velocity here. We've got constant negative velocity here, constant negative velocity there, slow velocity to the right, fast velocity to the right, some different ones here. Here's our changing velocity object accelerating. A trick here is just look at the beginning. You got that low slope, low velocity. Look at the end. You got that high slope, high velocity. Come a little further down. This object's got this low slope early on, and then it's speeding up negatively. It's got that high slope downward in the end. Here we've got that high slope in the beginning, downward, and that low slope in the end, downward still. All right. So moving on to velocity versus time graphs. So velocity time graphs show how velocity changes in the y-axis relative to time in the x-axis. Slope of these is rise over run again. Since rise is change in velocity and run is our change in time, the slope of a VT graph equals the acceleration. So what a velocity time does not show is the actual position of the object, just how position is changing. You can determine this change in displacement using the information from the graph and our equations. So what does the slope of a VT graph represent? Well, a positive slope for a VT graph is acceleration, positive acceleration. A negative slope of a VT graph is negative acceleration, or another way to put that is deceleration. So a flat line in a VT graph represents no slope, no acceleration. It just means we have a constant velocity, just constantly moving along at this velocity. But another thing we have to look at is, what does this area under a velocity versus time graph represent? Well, it represents our displacement, because if we multiply that velocity by time, we end up solving for our displacement from our velocity is displacement over time equation. All right, so let's talk about gravity for a second. So when a projectile is in the air under ideal conditions, its acceleration is around 9.8 meters per second squared down on most places on the Earth. We're just going to use that number to represent, a good enough number. All right, so if we kind of just round that number to 10, it makes things a little more uniform in this picture. But again, we'll still use that 9.8. But here we've got a subject throwing a ball up at 20 meters per second. Well, gravity is immediately slowing this ball down. Its acceleration is in the opposite direction of the initial velocity. Therefore, it's slowing the object down. And at its peak, that velocity is 0. And then, as it begins to fall back down, it starts to pick up that negative velocity. You'll notice the arrow on the left changes direction. Those are negative velocities now. And the ball returns at that exact 20 meters per second, but in a downward direction. He throws the ball up. It stops at the top, returns to him at an equal speed, but now directed down. The object thrown up will land at the same magnitude of velocity, but have that opposite direction. So what does this look like on a PT graph? Well, we're graphing that position. It's changing very rapidly at the beginning because we have that high positive velocity at the beginning. We have that no velocity at the top for just that split second. And then we begin accelerating to that very high negative velocity. Notice that slope here is positive 20. Slope here, negative 20. Slope near the top is close to 0, or 0 exactly at the top. The slope is 0. Here we go. On the right, you can see that slope being graphed out. 20 all the way down through 0, all the way down to negative 20. That's our velocity versus time graph for the ball being thrown in the air. These graphs are identical. These graphs are representing the same exact object traveling through space, but one is a position versus time, and one is a velocity versus time. All right, so what is the problem-solving process? Well, the optional step, but a very key step when you want to solve a problem. They say a picture is worth 1,000 words, right? So draw a diagram, draw a picture that illustrates what's happening in the problem, right? So you need to identify and label some unknown variables. You need to identify and label the known variables. And then based on what you know or you don't know, you need to choose the correct formula and rearrange that formula if necessary. Then use that chosen formula to determine the unknown variable. Wait until the very last step and round to the appropriate significant figures. Here we go. Here's all our formulas up to this point. So we've got our displacement, which is our final position, minus our initial position, our change in position. Right? We've also got our a squared plus b squared equals c squared Pythagorean theorem when we want to solve those displacements, and our displacement is in a triangular shape. We need to solve that hypotenuse, that's c squared. We need to solve it for c though, not c squared. When we talk about a circle, what is the circumference of a circle? It's 2 pi times the radius. Also, just pi times the diameter, since the diameter is 2 times the radius. We've got our speed down here, distance over time. Got our velocity, displacement over time. We can rearrange this or write it in different ways. Distance divided by change in time is another way it's seen. Change in position divided by change in time for our velocity. Again, anytime there's a change in something, it's the final minus the initial of that something with time here. All right. Then here we go with average velocity, the position final minus the position initial divided by time final minus time initial. All right, so acceleration, like we said, it was change in velocity over time. So it's our velocity final minus our velocity initial divided by time. It can also be written as velocity final minus velocity initial divided by time final minus time initial. And then we can use this to solve for time, right? Our time is equal to our velocity final minus our velocity initial divided by our acceleration. We can rearrange this to solve for our initial velocity. It's velocity final minus time times our acceleration. We also have our velocity final, which is equal to our time times acceleration plus our initial velocity. All right, moving right down. Here's our kinematic formulas. We've got that velocity final squared equal to 2 times acceleration times the displacement plus our velocity initial squared. More commonly, you'll see it written like this. Displacement is equal to velocity final squared minus velocity initial squared, all divided by 2 times a. Be very careful when you plug these into the calculator. Make sure that denominator is all in parentheses, or you solve the numerator first and then divide by that denominator value. Acceleration is our velocity final squared minus our velocity initial squared divided by 2 times our displacement. Again, we can, here they are, the other one is rearranged to solve for velocity initial. Velocity initial squared is equal to our velocity final squared minus 2 times our acceleration times our displacement. The key with these two over here, you want to solve for the square root of these two and then take into account that velocity could be positive or that velocity could be negative depending on which way, up, down, left, right, whatever you determine to be positive. You need to know what direction that velocity is, whether it be that final or the initial, to know which it is a positive value or a negative value. Here we can solve for acceleration, we can solve for displacement. We've got our velocity initial times time plus 1/2 our acceleration times time squared. Again, we can rearrange these and solve for our velocity initial. Here we can solve for our time when our velocity initial is 0, and we just know our displacement and our acceleration. All right, so that pretty much concludes what we've covered in the first 6 weeks. I know it was pretty quick and in a hurry, but you know, it's a lot of material to cover in this time period. So these formula sheets, they're all posted on the Schoology. So go ahead and don't be afraid to go over there and look at these if you need more time with them. All right, have a good one.